Today we're going to look at differential equations. Now, when we had differential equations, what was implied is we just find the antiderivative. So we had this dy by dx, this derivative equals 2e to the x, and basically we would just find the antiderivative of this. Now, we're going to look at this a little bit closer, and we're going to see the mechanics, or there's some mathematical steps actually involved to get from the derivative to the antiderivative. And we're going to make sure that we understand the process of this because we're going to start using this process a little bit more explicitly. So what's going to end up happening is we're going to find the dy, and essentially we're going to find the y, which is antiderivative. We're going to start by finding dy by taking the derivative function and multiplying it by dx. Okay, so we're going to do this. So this represents in our picture, if I had my f prime graph, my derivative graph, I'm just going to write this as y prime. Okay, I have my y prime, which is my derivative function here, times dx, and that's my change in area, which is the displacement on the antiderivative dy. So that's what we physically are dealing with. Algebraically, we're just moving the dx over to that side. And what we're going to do, and this is a little bit of a leap, but we're going to add up all the dy's on the left side, and we're going to sum it up, and we're going to say that's equal to y, and we're going to sum up all these y prime dx's, and we're going to have our integral. And this is how we get from our differential equation to our integral form, and then we can solve that by anti-differentiating. So let's do that let's do this a little bit more explicitly than what we've done before. So here we have a function y as a horizontal tangent at x equals 1/2 and x equals 0. So we have our derivative equal to 0 at those 2 points and has a x and y coordinate there. And we're given the second derivative. And so what's implied is we find the first derivative by anti-differentiating the and then back to the original function. But we're going to do this a little bit more explicitly. So we have d squared y, the second change of y, is equal to dx times dx, or dx squared. And that's equal to 4x plus 1. What I'm going to say then is the second change of y divided by dx is equal to 4x minus 1, and then times that by dx. And what we can then do is we can sum up both sides. And if I sum up this side, if I sum up the first changes in y, second change in y, I'm going to end up with the derivative function, dy by dx. And I anti-differentiate this side. I'm going to end up with x squared, 2x squared, plus x plus c. So we need to solve for c. We need to know when the derivative is equal to 0. It's equal to 0 at x equals 0 and x equals -1. So I'm just going to plug in x equals 0 there to solve for our c value. So dy by dx when x is equal to 0 is equal to 0 plus c, which is equal to 0. Okay, so this is our slope is equal to 0, so we get c equals 0. So now we have our first change in y, our first derivative. So we have dy by dx is equal to 2x squared plus x. And so again, what we're going to do is we're going to take this derivative function multiplied by dx. So we're going to move the dx to this side. And so we end up with this expression, dy is equal to 2x squared plus x times dx. And if we sum up this side, we're going to get y. If we sum up this side, we're going to get our integral. So going from here to here, we end up with y equals, if I'm going to anti-differentiate this, I get 2x cubed over 3 plus x squared over 2 plus another c, and then I'm going to use that coordinate to solve for c. So I know that y of 0 is equal to 12. And so when I plug in 0, I get c equals 12, and there I've got my y function. Okay, so there it is. So I haven't really done anything different than what we were doing before, other than I've introduced this new step. And this new step here, going from this step here to this step here, all I've done is I've moved the dx to the other side, and I've integrated or summed up, taken the sum of both sides. Same thing here. I have my differential equation. I just move my dx to that side algebraically, and I take the sum of both of those sides, and I'm going to get I'll end up with my antiderivative function.